This first review video is to go with the 2013 released form of the North Carolina final exam for physical science. So let's just jump right into it. Starting with number 1 here, we have a graph of distance versus time, and I noticed just by looking at it before I even read the question that we have a nice constant straight line. So the first thing that I think to myself is whatever this thing is moving with a constant speed. And so it wants to know, how does the speed of the cart compare at the time of 6 seconds to the time of 12 seconds. So we can go to the graph and look at 6 seconds. This is where we're looking at. And 12 seconds. I'll just draw a couple of lines to show where we're looking at right here. Now, we already said just by looking at the slope of this graph, the speed is constant, which means I know the speed at 6 seconds must equal the speed at 12 seconds. And so if we go down to A, the speed of the cart is at 6 seconds is greater than 12 seconds. Well, I know that can't be true if the speed is constant the entire time. The speed of the cart at 6 seconds is less than. Again, can't be true if the speed is constant based off of the graph. And so now we're down to C and D. The speed of the cart is half a meter per second at 6 seconds and 12 seconds. So we do have equal speeds here. And the speed of the cart is 2 meters per second at 6 seconds and at 12 seconds. So we've got it down to two choices that are equal. Now we just need to go up to the graph and calculate what the actual speed is. So that just basically means calculating the slope, because speed is distance over time, aka rise over run on a distance time graph. And so if we just plug it in for 6 and 12 seconds, at 12 seconds we have traveled 6 meters. At 6 seconds, we have traveled 3 meters. That is a time interval of 6 seconds. So I have 6 minus 3 meters divided by 6 seconds is 3 divided by 6, or 1/2. Choice C. Moving on to number 2, we have a chart of data that represents the change in velocity for 4 different trains. So the first thing I'm going to think about now when I look at this is change in velocity. We're talking about acceleration. If it took 5.38 seconds to reach the final velocity, which train had the greatest acceleration? And so what this tells us is we have the same time for all of the data, and we just need to look for the largest change in velocity. So for train W, we have from 60 to 91. That is a delta V of positive 31 meters per second. For train X, we have from 39 until 68. That is a delta V of positive 29 meters per second. Train train Y goes from 42 to 70. That is a delta V of positive 28 meters per second. And finally, train Z accelerates from 65 meters per second to 94 meters per second for a delta V of positive 29 meters per second. And so the greatest change, or delta V, in velocity for any one train was experienced by train W, or choice A. Why does a flat piece of notebook paper take longer to reach the ground than an identical piece of notebook paper crumpled into a ball? We have the flat piece of paper has more mass. Well, this would be false, because if we just took 2 identical sheets of paper from a stack, both pieces of paper would have the same mass. The crumpled piece of paper has more mass. Again, same reason, we can reject choice B. And now we have the frictional force of air has more effect on the falling flat piece of paper. Okay, let's come back and look at that. And the frictional force of air has more effect on the falling crumpled piece of paper. So we've got it down to 2 choices about the frictional force acting on the paper. And if we think about how the friction force is exerted against the paper ball versus the flat sheet of paper, the flat sheet of paper has more surface area to catch the air, which slows it down by a greater amount, than the crumpled up piece of paper, which has a smaller surface area and therefore catches less air and slows down less. So the friction or air resistance force of the air has a greater effect on the flat piece of paper because of its increased surface area. Number 4, why does the weight of an object change with increasing elevation on Earth? So when we're thinking weight, what we are thinking about is the force of gravity that is acting on an object. And between two objects, according to Newton's universal law of gravitation, the force of gravity is equal to some constant, so we can basically pretend that's not even there, times the product of the two masses divided by the distance between them squared. So if we were to work out this formula, we would see that increasing mass causes an increase in gravitational force, but an increasing distance, because it's in the denominator and it's squared, is going to have a decreasing effect on the strength of gravity. So if we increase the elevation on Earth, that means we are separating, so here's our small Earth, we are separating the second mass by pulling it away from the first mass. So we are increasing the distance between the masses, which means the weight is going to decrease. So let's see which answer choice this matches up with. The mass of the object decreases with higher elevation. Well, first of all, we're talking about weight, not mass. Mass is always constant. It does not depend upon force of gravity of anything, so we can reject choice A. The force of gravity acting on the object increases with higher elevation. Well, this is the opposite of what Newton's universal gravitation says should happen. As two masses are pulled away from each other, there is less force of gravitation between them. So we can reject B. The force of gravity acting on the object decreases with higher elevation. Well, that agrees with what we just found up here. So let's just check D. The mass of the object increases with higher elevation. Again, we switched back to mass instead of weight, and for the same reasons as A, we can reject choice D. Mass is constant, that is not affected by gravity. So we're left with choice C. Which type of friction occurs when an eraser is rubbed across a sheet of paper? So we just have a list of different types of friction. Static friction, between things that are at rest or not moving. Well, if we're rubbing it, it is clearly moving, so we can reject static. Sliding friction, well, if I slide a pen across the paper, that's the same motion as rubbing an eraser, so let's just start that and come back and check. Rolling friction is for objects that are rolling across a surface, so we don't erase things by rolling the eraser across the paper, so we can reject that. And then fluid friction is friction that's within a fluid. So for example, water or air are both examples of fluid, this one being a liquid, this one being a gas. So air resistance, water resistance, those are fluid friction. And clearly we don't have any of that at play here, so choice B is the correct answer. Number 6 says two students are pulling on the opposite ends of a rope, but neither student is able to move the other. Which statement best explains why neither student is moved? So we have two students who are pulling with equal but opposite forces through a rope. So force 1 and force 2. So let's look at our choices here. Choice A, they each pull on the rope with the same amount of force, so the net force is 0. Okay. They each exert the same amount of friction against the ground, so the net friction is 0. The forces are not balanced, but gravity keeps them from moving. Or the two students have the same mass. Alright, so first of all, let's get rid of choice D, because this statement has absolutely nothing to do with the question at hand. We can't say anything about their masses based off of these horizontal forces on the rope, so we just can't determine anything about choice D. Moving backwards here, Choice C, their forces are not balanced. Well, if their forces are not balanced, that means they would be accelerating. And acceleration is not the same thing as at rest. Since we are not moving, neither student is moved, then we know we cannot be accelerating, and so there goes choice C. They exert the same amount of friction against the ground, so the net friction is 0. Well, choice B actually contradicts itself. If they're exerting the same amount of friction against the ground, then the friction involved in the system is clearly not 0, since there's some friction between each of the students and the ground itself. So the friction itself is not 0. I mean, indeed, if the friction was 0, this would not work at all. So we're back with choice A. They each pull on the rope with the same amount of force, and so the net force is 0, which makes sense. This fits our scenario. Number 7. The diagram below shows a board on top of 2 bricks, let me pull that down, with a cylinder on top of the board. The board exerts an upward force of 50 newtons, which best explains the situation. So we know the force of the board, is equal to 50 newtons upwards. Alright, so now we have 4 choices here. The board has a weight of 50 newtons, the cylinder has a weight of 50 newtons, the combined weight of the 2 bricks is 50 newtons, and the combined weight of the bricks, board, and cylinder is 50 newtons. Alright, what this is relying on is Newton's third law of motion. And so the board is exerting a force of 50 newtons up. Well, if we examine the board, that means it is at rest. We have another force balancing this out, 50 newtons down. What's causing the downwards force on the board? Well, the only object described in this diagram to exert a downwards force on the board is the cylinder. So we'll call that force of the cylinder. And since this force of the cylinder is what's causing that 50 Newton reaction from the board, we can say that the cylinder has a weight of 50 newtons. We can't say anything about the bricks because the bricks are underneath the board, and therefore the interaction between the board and the bricks is not going to tell you anything about the weight of those bricks. We can only tell about the cylinder. Number 8, which is an example of a mixture. So we're looking for something that is not pure, so we can't find it on the periodic table, and it doesn't have a chemical formula like a compound. So we have iron filings, so basically just shave down iron. Iron has its own chemical symbol. It is an element, and elements are substances. Another way of saying substances is that they are pure, and pure things are not mixed things. So we can eliminate A. Copper wire, so we have copper metal that's been drawn into a wire form. Well, copper also has a chemical symbol because it is an element. Again, a pure substance is not the same thing as a mixture. Bronze pipe, all right, so when we're talking about bronze, we're talking about a metal alloy which has 2 or more metals that have been blended together physically. So that is definitely a possibility. Metal alloys tend to be what we call solutions. Solutions are mixtures. They are homogeneous, meaning we can't look at individual parts of it and see how they are different from the other parts, but it is multiple elements that are blended together. And titanium, again, has a chemical symbol. So like A and B, we can eliminate it because it only has one pure substance and not a combination of them. Number 9 says an element located at group 18 and period 4 would be classified as which type of substance? So just for reference here, let me pull out my periodic table, same as the one that you're going to be given at the final exam. Group 18, so we're looking at the noble gases. And the fourth period, so we go 1, 2, 3, 4, we're looking at the element krypton, element 36. So let's return to the practice test here. Alright, so how would we classify something that is in group 18? Well, the noble gases are not the same thing as halogens. That would be group 17. So we can eliminate that. A metalloid would be located along the staircase on the periodic table, so we can eliminate that. A lanthanoid is a rare earth, or as we call them, inner transition metal, found along the bottom side of the periodic table after the element lanthanum. So lanthanum down here, element 57 on the left-hand page of the periodic table. So the lanthanides right here along the bottom. So cerium all the way through that part of the periodic table, so we can eliminate that. Or a non-metal. This one is true, because all the noble gases are non-metals found on the right-hand side of the staircase. On the left, of course, being the metals, and on the staircase itself, except for aluminum, we find the metalloids. Alright, number 10, we have a chart showing the density of 5 different gases. Helium, neon, argon, krypton, and xenon. So the gas has a volume equal to 4.52 liters, and if its mass is 8.05 grams, we want to know what the identity of the gas is. And so we can tell that we need to calculate the density of this gas. We need to figure out which gas has the property that we're looking for that matches up with these two properties. So density is mass divided by volume, and if we don't remember this, we can always go back to our reference tables. There it is. On the back side of the formulas, we have density equal to mass divided by volume, or if you didn't want to flip back and you forgot the formula, you can look at your units. Grams divided by liters. Well, grams is just mass. Liters is volume. And we are given information in grams and liters, so we must just need to divide 8.05 grams by 4.52 liters. So let's put that into our calculator right now real quickly. So we go 8.05 grams divided by 4.52 liters, and we get a density of approximately 1.78 grams per liter. So we want to compare this to our table of densities and look for a gas that has the property of having a density of 1.78 grams per liter. And we see that the gas argon has a density matching the given volume and mass, so we can say that with confidence that this is the element argon. Alright, number 11. We have another graph here showing us the solubility curves for various ionic compounds. So it's just like that solubility curve we looked at in class, except with far fewer elements to make it a little easier to follow along. And we want to know, at which temperature does potassium chloride have the same solubility as copper 2 sulfate? So basically they're asking us to find, in math terms, the intersection of those two lines here. So we find potassium chloride's line. I'm just going to trace it, even though you probably won't be able to see the trace on the camera after I do that. And then copper 2 sulfate is this line right here. Okay, they intersect at one point, which I will estimate on the graph by finding our temperature and our solubility. Alright. Now we want to know at which temperature does potassium chloride have the same solubility. I could say what that solubility is, but we are just interested in the temperature part, and so we're going to follow the x-axis crossing here between 70 and 80, and there is only one answer choice that makes sense, 73 degrees Celsius. None of the rest of them are even close. Alright. Number 12, we have an electron dot diagram for some unknown element X here, and we want to know which element it could possibly represent. Now we're given a choice between boron, phosphorus, sulfur, and bromine, but let's just look at our dot structure. We have 1, 2, 3, 4, 5, 6, 7 valence electrons. And what that tells me is I'm looking for an element in group 17. Alright, so we're looking for a halogen. Now I happen to know, of course, that that is bromine, but if we look at our periodic table, group 17, fluorine, chlorine, bromine, iodine, and astatine. The only one matching one of our answer choices, of course, is bromine, so we can eliminate the rest of them. Just to double check, show you another way we could look at this, boron is in group 13, so would have a dot diagram that looks like this, 1, 2, 3. Phosphorus is right under nitrogen in group 15, so it would have 5 dots, 1, 2, 3, 4, pair at the 5th, and sulfur is directly under oxygen in group 16, and so it would have 6 dots. It would look like 1, 2, 3, 4, 5, and 6, with 2 that aren't paired, leaving us with bromine with the 7. Alright, number 13. This diagram represents a neutral atom of boron 11. How many protons and neutrons does boron 11 have? Now, of course, we could just go ahead and count how many electrons, how many protons, and how many neutrons. So we could just do this. 1, 2, 3, 4, 5 electrons. 1, 2, 3, 4, 5 protons, and those should match. Indeed, they do. And then 1, 2, 3, 4, 5, 6 neutrons. All right, and so we have 5 protons, 6 neutrons. That would be choice D. Or we could also recognize that if we're looking at boron 11, I'll write it another way here. Boron is the 5th element in the periodic table of elements, which means it must have 5 protons. One more or one less, it would no longer be boron. 5 protons means it must have 5 electrons in order to represent a neutral atom and not an ion of an element. And then to finally get the neutrons, I have a mass number, which was given to me in the isotope notation, boron 11, so it has a total mass of 11. Subtract the protons, which contribute to the mass, leaving us with 6 of the other particle that contributes to the mass, neutrons. Still gets us to choice D, of course. Alright, number 14, which 2 elements have the same number of valence electrons? So valence electrons, we should automatically be thinking it is determined by the group number on the periodic table. So we're looking for 2 elements that are in the same family, so up and down column on the periodic table, and not left and right horizontal periods. So we have calcium and, carbon and oxygen. Getting ahead of myself there. So carbon and oxygen, they're in different groups but the same period, which means we can eliminate them. Sodium and magnesium. So find sodium, it's an alkali metal. Magnesium, an alkaline earth metal. So they are in different groups, same period, we can eliminate them. Chlorine and fluorine. Fluorine and chlorine, look at that. We have 2 elements in the same group. And gallium and germanium, 2 different groups, same period, and so we can eliminate that. And of course, if you weren't sure, couldn't remember if it was group or period that determined the electrons, you could just go through and find all of these pairs of elements and compare them, and you would quickly see that these three have in common a period, while this one has in common just this group, making this one the likely answer choice since it is the only unique choice. Number 15. Which of these elements is the most chemically reactive? So most reactive. So I'm automatically thinking on the left side with the metals in group number 1. The most reactive element is found at the bottom, and for the nonmetals, group number 17, the most reactive element is found at the top. So now we have zinc, iron, potassium, and germanium. Well, if we start with zinc, zinc is a transition metal, so it is more towards the right-hand side. If I squeeze in the other part of the periodic table here, the most reactive metals are all the way over here. So we can eliminate zinc as a transition metal, not terribly reactive. Same thing with iron. If we find iron, it does a little better. It's actually on the right page of the periodic table now. So it's a little bit closer to the reactive alkali metals, but it is still very far off as a transition metal, so we can eliminate that. Now we're left with potassium and germanium. Well, potassium is in group 1, so that is a pretty reactive family. The only thing that would usurp potassium as being the most reactive is if we found rubidium, cesium, or francium, because, again, the more reactive ones are at the bottom for metals. But we do not have one of those elements. We only have germanium. So we know it's got to be C, but just to show you where germanium is, it is all the way over here. It is a metalloid, so it is definitely not one of the most reactive elements. It is far, far away from that. Alright. Some coins are alloys of zinc and copper. Which type of bond forms between these coins? So we've looked at ionic and covalent so far. We have not hit the third type of bond, which is metallic, but we could get through and eliminate some of these anyway, because zinc is a metal, copper is a metal. Metal plus non-metal is what is required for an ionic bond, so we can eliminate C. Non-metal plus non-metal is what is required for a covalent bond, so we can definitely eliminate covalent here. We're left with hydrogen and metallic. Hydrogen bonds are not something we really talk about much until chemistry, but suffice it to say they are very weak forces between certain molecules, such as water. So if I drew up a couple of water molecules here, there would be some weak attractions formed between the oxygen and the hydrogen of different molecules, nowhere nearly as strong as the covalent bonds that are actual proper chemical bonds that make up the molecule of water. They're just some slight weak attractions between the oxygen and hydrogen because water is a polar molecule, meaning the oxygen is a little bit negative and the hydrogens are a little bit positive, and of course opposites attract, so even though it's a partial positive and a partial negative, they are still going to attract each other. So that's what a hydrogen bond is, in the unlikely event that you run into that again. So we can eliminate that. And if we had not known that, and we're just left with hydrogen and metallic bonds, well, we know zinc and copper are both metals, which makes this a very good candidate to choose. There's only one thing that makes sense when you're attaching two metals together. Alright. How can two different nonmetals form a compound? So two different nonmetals. We have nonmetal plus nonmetal. So I should think covalent. Co as in share, valent as in valence electrons. So we are sharing electrons. So there goes A. We're never sharing protons because they're buried in the nucleus far, far too deep beneath all of those electrons to ever be important for chemistry. By sharing electrons, yes. By transferring protons, again, protons, we can just eliminate that automatically for chemical bonding. I don't know why I circled A over here when I checked B. And then by transferring electrons. Well, transfer implies ion, aka ionic bonds, so we're not doing that. It is B. Which is the chemical formula for magnesium hydroxide? Well, we come to our periodic table in case we don't remember our symbols. Magnesium is Mg. It is an alkaline metal, alkaline earth metal, excuse me. So Mg, since it is in group 2, I'm going to write a +2. And then hydroxide is not an element, but a polyatomic ion. And so instead of looking at the periodic table, I am going to find in my reference tables this chart of polyatomic ions. And hydroxide is oxygen and hydrogen with a -1 charge, so OH -1. So let me write that over here. OH -1. We would do our crisscross, so this 1 comes down here, this 2 comes down here. Now, we might be tempted to write it like this, MgOH2, because there's no extra number here to get things confused. But if I wrote it like this, I would be saying OH2, which is the same thing as saying H2O. 2 hydrogens to 1 oxygen. What I really want to say is 2 hydroxides, so I need to make sure there are parentheses around that hydroxide so I don't accidentally write the formula for water in some strange new way. So we have MgOH subscript 2, and the OH being in parentheses. Alright, so what's wrong with these other formulas? Well, magnesium has a +2, hydroxide has a -1. This compound has a charge overall of +1, so 2 plus -1. Compounds have a charge of 0. They are neutral, so we can eliminate B. MgOH subscript 2 has the error that I just talked about over here at the parentheses. I have 2 hydrogens to 1 oxygen, which is not the formula for hydroxide. It is OH, no subscripts, so just one of each. So there goes that. And then Mg2OH, well, 1 magnesium is a +2, so 2 magnesiums would be a +4. Hydroxide, if we look it up in the table again, is a -1. This compound has a charge of +3, so we can eliminate that because that is not equal to 0. What is the correct, or which is the correct name for the compound NaNO3? So we're going to name what we see. First of all, I have 1, 2, 3 capital letters. That tells me there is at least 1 polyatomic ion floating around in here. So Na, I know, is sodium. And indeed, all 4 answer choices start with sodium. So we don't really care about the Na, we care about the NO3 part. So if we look up in our table, because we determined already that it's a polyatomic ion, NO3, we see that it has the ending nitrate, ATE. So I would write nitrate, like so. And we find that this would be choice A. Sodium nitrous acid. Okay, we didn't talk about how to name acids, but sodium nitrous acid is not a potential chemical formula. It doesn't look like anything we've named in class. Sodium nitrogen oxide, you would be naming each of the 3 elements, so sodium Na, nitrogen N, and then oxide. They're trying to trick you by putting the "ide" ending on the end here, like we did with the binary compound, so only 2 elements. So that's a no-go. And sodium nitrogen trioxide, they're trying to trick you with the covalent prefixes. Indeed, you do have 3 oxygens, but this is only for covalent compounds. So sodium is a metal, which means you should never use those prefixes anywhere in the name. So we can get rid of that, and we're left with sodium nitrate. Which is a correctly balanced chemical equation. So this is something that we're going to be looking at this week, but a balanced chemical equation simply means the same number go in as come out. So reactants are equal to the products. So we can simply look and count the atoms on each side of the chemical equation and see if they are equal to each other. If they are, it is balanced. If they are not equal to each other, then it is not balanced. So I just start with whichever element falls on the left side, and then if that's good, then I check the next element until I find one that doesn't work, which means the whole thing must not work. So here, for example, I have one atom of copper on the left-hand side. So I come over here and I look, I have one atom of copper. Good so far. So Cl2 means I have 2 chlorines. Coming over here, I have Cl3, and it's multiplied by a 2, so I have 6 chlorines. So that is definitely not balanced, because 2 does not equal 6. Again, starting with left to right, 2 coppers, so 1 copper times 2, copper, 2 chlorides, so that's 2 coppers. Coming over here, 2 coppers, good so far. Cl2, so 2 chlorines times 2 copper 2 chlorides, so 2 times 2 is 4 chlorines going in, and coming over here we have 3 chlorines times 1 is 3, so 4 is not equal to 3. We can eliminate choice B. Repeating, 2 coppers go in, 2 coppers come out, good so far. 2 times 2 chlorines, so 4 chlorines go in. 3 times 3 chlorines, so 9 come out. Again, 4 is not equal to 9, so we can eliminate choice C. And finally, let's just make sure choice D is correct. 3 coppers, that's good. 3 times 2, or 6 chlorines. 2 times 3, or 6 chlorines, that's good. And 2 times 1 aluminums is 2 aluminums. 2 times 1 aluminums, 2 aluminums. So everything is equal in choice D, which makes it correctly balanced. All right, number 21. We have an equation representing an unbalanced chemical reaction, so there's no coefficients thrown in front of it yet. When the equation is balanced, which coefficient should be placed before NaCl? So I'm just going to go ahead and balance this equation down here. I'm going to rewrite it first. So we have NaI, sodium iodide, plus Cl2, chlorine, produces sodium chloride, NaCl, plus iodine, I2. And I'm going to do a little inventory of my atoms. I have sodium, I have iodine, and I have chlorine. Going in, I have 1 sodium, 1 iodine, and 1 times 2, or 2 chlorines. Coming out, I have 1 sodium, 1 times 2, or 2 iodines, and 1 times 1, or 1 chlorines. So if I look at this, I need to balance this iodine first. If I just go from top to bottom, I'm going to stick a 2 in front of sodium iodide. That will give me 2 sodiums going in and 2 iodines going in. Iodine is now balanced, sodium is not, so I can throw a 2 in front of that as well. 2 times 1 sodium is 2 sodiums, so that balances. Now we have 2 times 1 chlorine, and that brought the third part into balance just by solving the first part. So we have 2 in front of NaCl, so choice A. Or if you didn't want to balance the entire equation, of course, you could literally plug in the coefficients and then just see if you get equal amounts on both sides. 22, this equation represents a balanced chemical reaction. So we have all of our correct coefficients. So that means since there's nothing here, we have a 1, the 2, and a 1. Which type of chemical reaction is represented? So we're just looking for patterns here. I have a compound plus a second compound producing a new compound and a second new compound, which matches up with our double replacement. For it to be single replacement, one of these reactants would have to be just an element instead of a compound. Since they're both compounds, we can eliminate the single replacement part. Decomposition, there would only be one thing on the reactant side, forming 2 or more things. And then synthesis, we would have 2 things going in, but then we would just have the one thing coming out, so we can eliminate that as well. Alright, almost finished here. Number 23. A scientist uses litmus paper to measure the pH of several different solutions. Which solution turns the litmus paper red? For litmus paper, all you need to remember is that blue is for base and red is for acid. So blue pHs would be greater than 7. Red pHs would be less than 7. So if we look over here, it wants to know which one of these is an acid. Hydroxide, that is a base. NaCl, that is a salt. HCl, hydrogen, and the front part here, that is an acid. And then NH3 is actually NH3OH when it's in water, which is a base. And so the only thing here that would be turning our litmus paper red is hydrochloric acid, HCl, or choice C. The equation in number 24 represents a balanced neutralization chemical reaction. So neutralization refers to neutralizing the pH, so an acid plus a base. A solution of which compound has a greater pH than 7? So greater than 7 means I'm looking for the base. Those are pretty easy to spot. They pretty much always have this hydroxide at the end here. So that is our base. Excuse me. And hydrofluoric acid is our acid. So if we come over here, a solution of which compound has a pH greater than 7, water, because it is neutral. Well, that would mean it has a pH equal to 7, so it already can't be true. Hydrofluoric acid, because it is an acid, but we're looking for a base, so we can eliminate that. Lithium fluoride, because it is a salt. No, we can eliminate that. Lithium hydroxide, because it is a base, which is true, because we were looking for the base. So you didn't even have to match it up with individual chemicals. You could have just gone through here and we would have gone acid, salt, base, and neutral. And of those four things, only a base would have a pH greater than 7. Number 25, which group is in order of increasing ability to penetrate an object? This is referring to nuclear radiation. Alright, and we have alpha, beta, and gamma radiation, represented by their Greek letters here. Alpha, which is just the nucleus of a helium atom with a charge, is very damaging if you ingest it, but cannot penetrate very far. So this is low penetration. Beta, which is just an electron, basically, so 0 over negative 1 e, has a medium penetration power. So alpha would be stopped by your skin, a sheet of paper. Beta you could stop with a piece of aluminum foil. And gamma radiation, which is just photons of high energy light at the gamma end of the spectrum. So let me just flip to my electromagnetic spectrum for 1 second. Gamma rays are all the way over here at the high energy, short wavelength, high frequency side of the spectrum. So they have the most penetration power. So if we go back, we wanted to list it in the order of increasing ability, so low to high, so we want alpha, beta, gamma. So alpha, proton, beta, well, proton, that's an odd place to find that word listed, it's not a type of radiation. Alpha, beta, gamma, yes. Beta, no. Proton, definitely not. Gamma, beta, alpha would be the reverse. Oops, I don't know why I just circled that. So that would be choice B, not choice D, the one that I checked. Choice B is the correct one. Alright. 26. A 100-gram sample of radium-226 has a half-life of 1,600 years. How long will it take before there's only 12.5 grams of the radioactive radium-226 remaining? So every 1,600 years, we're going to have half of what we started with. So if we start with 100, and then after one half-life, we wind up at 50, After 2 half-lives, we wind up at 25, and after 3 half-lives, we wind up with 12 and a half. So that was half-life 1, half-life 2, half-life 3. So if 1 half-life is 1,600 years, and I have just experienced 3 half-lives, I'm going to be multiplying 1,600 times 3. And of course, that's going to come out to be 4,800 years, or choice C. Why does a student's hand feel cold when holding an ice cube? So if we represent our hand with a line and our ice cube with a box sitting on top of it, when you're holding an ice cube, of course, the ice cube has a lower temperature than your body. So let's just say your body temperature is about 98.6 degrees Fahrenheit, and an ice cube temperature is about 32 degrees Fahrenheit. Heat is going to flow from hot to cold, which means heat is going to flow out of your hand and into the ice cube, which is what you perceive as coldness. So if we look at our choices, heat flows from the ice cube to the hand. Well, if heat were leaving the ice cube and going to the hand would be getting hotter. And that is not true. Heat flows from the hand to the ice cube, yes. Let's just check the other two. Cold flows from the hand to the ice cube. Cold is not a thing in physics, and the same thing happens in choice D. Cold flows from the ice cube to the hand. We measure all things about thermodynamics in terms of heat. You can have more heat or less heat, but you cannot have something called cold. Cold would just be heat is exiting your system. So if you're from the perspective of the hand, heat is flowing out of you and into the ice cube to make the ice cube warmer. There is no such thing as coldness in physics, just less heat, so we can eliminate C and E, leaving us with just B. What happens to the molecules in a pot of water as it is heated? Number 28. So as we heat water, we are putting energy into it, of course. So we're on a heating curve, like so. We're in this part of the heating curve, which has that increasing positive slope because we're making it hotter. We're going to have an increasing temperature. And increasing temperature means things move faster, which is choice A. Slower would be removing heat, making it colder, cooling it down. So maybe if you stuck it in a fridge, they lose thermal energy. Well, losing thermal energy is the opposite of what you do when you heat something. Or they gain potential energy. That would refer to this part of the graph right here, this flat line. That would be a phase change. So the next phase change, since we're in liquid water, would be boiling. So liquid to gas. Freezing and melting and condensation are also phase changes, but if we're heating something, liquid water in a pot, or we would be referring specifically to boiling as the next possible phase change, and in which case you would be gaining potential energy. However, we did not specify that we are actually boiling, we simply specified we are heating the pot of water. So the only thing we can say with confidence is that they will be moving faster, because we do not have enough information to say if it is boiling. Number 29. Two boxes, X and Y, are on a shelf 10 meters above the floor. So let me go ahead and draw my shelf. 10 meters, X and Y. Box X has a mass of 4 kilograms. Box Y has a mass of 8 kilograms. Which statement best represents the relationship between boxes X and Y? X and Y have no potential energy. Well, potential energy is just mass times gravity times height. So in this case, they're both 10 meters off the ground. One has more mass than the other, so we know box Y is going to have more potential energy. And in fact, we know it has twice as much because it has twice the mass. And gravity is a constant, so we can just pretend it doesn't happen here. So they have no potential energy is a false statement because they are off the ground. Box X has less potential energy than box Y. Indeed, it has half of that potential energy, so that's true. Box X has more potential energy than box Y. No. Box X and box Y both have 784 joules of potential energy. We could calculate the potential energy of X and Y, but there is no point because it says they both have the same potential energy. If they both have the same height, and of course gravity is a constant, then that implies they have the same mass. They do not have the same mass, as the problem told us. One is 4 kilograms and one is 8 kilograms, so we can just eliminate that outright. So choice B is the only answer that makes sense. Alright, number 30, which describes the kinetic energy of a ball that is in free fall, so the only force acting on it is gravity. We tend to pretend air resistance does not happen in real life because it's such a small value compared to your gravitational force for many objects, such as balls. So choice A, the kinetic energy remains the same while the velocity increases. Alright, so the velocity is going to increase for a time in free fall until you hit your terminal velocity. So that can happen for part of your fall. The kinetic energy is going to decrease because the velocity increases. That statement doesn't make any sense. Kinetic energy is 1/2 your mass times the square of your velocity. So as velocity gets bigger, kinetic energy has to get bigger. So choice B just makes no sense at all. The kinetic energy increases because the velocity increases. Alright. So we do have an increase in velocity for part of the time you're in free fall. And increasing velocity would, in fact, increase your kinetic energy. Or the kinetic energy remains the same while the velocity decreases. Well, any change in velocity means your kinetic energy cannot remain the same. So choice D has to be eliminated. So we have the kinetic energy remains the same while the velocity increases. Okay, again, cannot happen. Because any change in velocity would change your kinetic energy. So the only one that makes any sense is choice C. How do radio waves and visible light waves differ? So we're looking at electromagnetic radiation. So two different types of light, one visible and one not so visible. So here's our electromagnetic spectrum that we should be referring to. Visible light, I find between 10 to the minus 6 and 10 to the minus 7th meters. And radio waves, 10 to the 4th through 10 to the 0, or just 1 meter. So radio waves have long wavelengths compared to